Yeah. I thought it'd be useful to start by giving a brief overview of the network, where we are now, and what's to come, particularly with Control Period 5 on the horizon. So, brief summary of the UK rail infrastructure: around 10,000 route miles of track, 18,000 passenger journeys and 1,000 freight journeys every day, 2,500 stations, 7,000 level crossings, 17,000 signals, 670 tunnels, 15,000 overbridges, 20,000 underbridges, and 2,000 viaducts. So you can see that's a significant amount of infrastructure to look after and maintain. So, tamping. From a number of presentations that I've seen and various documents I've read over the years, it's clear that the rail infrastructure is viewed and managed more and more as an asset. This applies to track in particular, and over the years tamping has proved more and more critical to managing and maintaining this asset. The reason that we tamp, to achieve the correct line speed, we need the correct horizontal and vertical alignment, top and line. Tamp has started to appear in the UK from the early 70s, and since that time, with faster speeds, reduced access, heavier rail and so on, tampers are now the first choice for maintaining that alignment. So when maintaining the track, we've got a number of options. We can simply put it back to where it was. This can be done by a variety of means. First of all, we can measure off the adjacent line with lasers, cant sticks, levels, tapes, etc. Although there are some sites where that proves more challenging than others. We can also measure from fixed datum plates on structures, providing that they are known to be up to date. And very often now, though, we see the use of more 3D survey techniques like robotic total stations, particularly where a redesign has been done, such as for a line speed improvement scheme. So tamping is needed in three areas of track alignment: maintenance, renewal, and as-built. And over this presentation, we'll cover the first two, maintenance and renewal. I thought it might be nice to look at some figures taken from Network Rail's strategic business plan, put together in January 13, showing the amount of money spent through Control Period 4 and projected into Control Period 5 for maintenance. As you can see, the number gradually decreases, which will break down to a number of factors, not the least of which the amount of money that's been spent on the infrastructure over the years, which is now starting to pay off. We're starting to see return on our investment, as it were. In terms of the track, you can see the breakdown of costs, but the expenditure over the next few years is set to drop down with a slight rise in 2016 to 17. With the higher demands on the network, technology and processes like the ones I will talk about during this presentation will help to achieve these goals. So if we look at the railway life cycle and concentrate on the safety and maintenance aspects of that, and in particular the rail asset management, the aim of this presentation is to show the relationship between the digital design process through to construction and then track realignment and maintenance. So we can take our 3D digital design elements, horizontal and vertical, and actually build up a 3D model of the formation and the design of the ballast levels. From there, we can then take that 3D digital file and via USB stick put it into a machine. And this is what we can see inside the driver's cab. We've got the background digital design file showing the layout of the shoulders and the track, and the driver can see the amount he has to move the blade on the left and the right as he drives along. We can use exactly the same 3D machine control system linked into a total station as shown in this slide, or with a GNSS system as shown in this picture here. And it can be switched around between machines to suit. When we go out with the machine, in this case a dozer, putting in some ballast, the driver can select the tip of the blade that he wants to work with, and from there he can then stake out the position of the shoulders. And importantly, he can also put in the gradients for the two roads to the required level. This means that when we come to offer up the track, the ballast is at the right level to accept it, and we can then minimize the tamping process. By then using the track measuring device, we can create our ALC files and digitally transfer that data into the tamper. So one of the biggest issues with the modern network really is how long we have on site to do all this work. So productivity is very important. If we look at a traditional rail shoe, typically around 350 meters per hour. If we use a track measuring device, 600 to 800, and trying to keep in front of tampers, we need to improve that process still further. So how can we do that? Some of the requirements for the tamping process, the issues that we've seen can be the time lag between the original measurements of the track position and the tamping process. So we need live data if we can. We need to keep in front of the tamper and keep it working. The system needs to be simple to use. It needs to be highly productive, and it also needs to be very accurate. In essence, it's all about speed, and the answer to that from our perspective is the Judo Forces system. So what we do is take the total station from a tripod, put it onto a second track measuring device, and use them in tandem live in the field. The development of the Judo Forces was started back in 2005-2006. It's been available as a standard solution worldwide since 2008, and it was originally designed to achieve 1,200 meters per hour. Essentially, the system consists of two track measuring devices, which have sensors for measuring cant and gauge. They're linked together, so the two TMDs are talking with each other. The total station is locked onto the target, so it's measuring the position of one TMD in relationship to the other. And we also have a standard triple control unit talking to the total station and receiving the data from both TMDs. On top of that, we have the Judo Forces software, which sits on the control unit, and Judo Office and Judo TAMP software, which sits on a PC or mobile tablet. So if we look at taking the digital design and converting it into a format for the field use, this particular example shows us using BRT, Bentley Rail Track, to bring in a design. So the first thing we do is create a new project, and we click on the Forces button here to create that. And once we've created our project, we import the data. We use XML as a data format because it maintains the geometry integrity, and it's also very easy to disseminate. And when we pick the XML file, we can see it's split into the three components there: horizontal, vertical, and cant. We can then select which of those elements we want to bring in, click OK, and then we can see in this particular case we brought in 3 railroad alignments. We can click on the horizontal alignment, the vertical alignment, and the cant alignment. So that's is all that's required to bring that data in. We can also key in the data manually, but 9 times out of 10 there's no need. All that information is contained within the design, and it's a simple process to import that information. What I'd like to talk through now is a workflow example. So I'll talk about taking the design file. In this case, it will be from MX Rail, not from Bentley Railtrack. So you'll see the import of that data. I'll then talk through the operation of the equipment in the field, and then also talk about the reporting once we've taken that measured data. It might be worth mentioning at this point, if any questions do come into your mind, it might be an idea to jot them down, and we will be taking questions at the end. So, taking a digital design file, we take the XML file, and we also take a list of control coordinates, and we bring those files into the GDEV Office software to prepare that data. So just as before, we'll go on to create a new Vorsus project and import and create that there. We'll then import the XML file, just as we did before. In this particular case, we'll just select one alignment, and we'll also bring in the list of control points too. Once we've brought that information in, you can see it along the tree view there on the left-hand side, just as before, the horizontal alignment, vertical alignment, and cant alignment. We've also now got the control coordinates underneath the reference points list. And what we can now do is click on the alignment button and create a new alignment. Give it a name. And then, hidden away from view in actual fact under this particular screen, is the fact that we then drag and drop the horizontal alignment, vertical alignment, and cant alignment into their respective areas below here. We also drag the rail survey control coordinate lists into its respective area here, and then we right-click, click on export, and we export that data. In this particular case, we're going to export it as a geo file. So that's one of the files that would be required as part of the sampling process. So we send it out as an ALC geometry geo file. Another thing that we'll do at this point is take those components, the horizontal, vertical, cant, and control coordinate list, and copy those onto a memory stick to transfer them onto the control unit. So once the data is transferred onto the controller, we can then go out live into the field to measure with the track measuring device. When we're in the field, we support a number of different coordinated points, either pheno markers in the ground, ATG bolts, it could be survey nails, any markers at all. As long as they've got a coordinated relationship to the design, we can support it. Now, what we're talking about in this particular example is an absolute track geometry design where we have coordinated design for the track alignment and for the control points, but we can also use the Vorsus system in relative mode. So I know there are areas of the track where we would have reference points with known chainage and offset relationships to a design that are not actually coordinated. That's fine. We can still use the Vorsus system in those environments as well. So we can use it in absolute track geometry and also in relative track geometry mode. Okay, so once we've got out into the field with our controller, we can connect to the total station and we can click on the alignment files, and then in the alignment files area we can pick the relevant horizontal, vertical, and cant geometry files. We can also select our reference points file. And the latest version of the software, due out in a few months, and going through beta testing at the moment, we're actually using a database system. So rather than going through this particular process, we would simply copy the whole database that we've created from the Office software onto the controller, and all that information would be pre-prepared. We wouldn't have to click on this step in the field, but this is how we're doing it currently. We then click on Start, and the system then calculates the alignment relationship between the design and the control coordinates. We can then select a tamping run. So this is a file that will store the measured data. So in Germany they have a variety of set tamping runs and tamp in a certain order, and they will store that data under each of those tamping run names. We do a similar thing in the UK, but it's really just creating a file name. So in this case, as we measure in the field, that data will be stored under the process.DUA file name. And that's the file that we'll download into the Office software once we finish our measuring process. At the first time we use the equipment, at the start of the shift, we would calibrate the inclination in the gauge sensor. It doesn't need to be done after every setup, but simply at the start of each working shift. That's a fairly straightforward process, so we would undertake that. Once that was done, we could then commence the measuring process. So what we've got here is a section of track with the two track measuring devices. The lead one has got the total station on. The one to the left has got the prism on. We've got a couple of reference control points, whether they be ATG spigots or ground anchors, and then we've got our Office software on the control unit. So the first thing we do is we've already connected to our total station. We would now define the chord, and to do that, we move our track measuring device with the total station on to the first reference point, and we take a measurement to it. That measurement is displayed with a yellow box around it, and once we click Store, a green box appears, and we've now stored that information. And you can see here the delta lateral, delta heights, and delta cant. That shows the relationship between where the track measuring device is now versus the design. So we've already taken the first measurement in the tamping process. So we now move the track measuring device with the total station on opposite the second reference point. We lock it down, mark the track as we did before, and measure to our second reference point. And that then repeats the process. So we can see now we're 1 millimetre away from design in this particular instance. We now move the prism TMD over the first mark point and measure back. And that then displays the same relationship that we had before, so we know we're referenced at the same point, and all the control measurements that we've taken have all tied in. Because we know the vector between the two reference points, we know the offset vectors that we've measured with the total station, and we know that the fourth vector we've just measured now, the whole system is referenced on the track. And we can simply now click onto measurement and begin that measuring process. So we now move the prism track measuring device towards the total station, either measuring at regular intervals in stop and go mode, or we can also support fully kinematic, where we simply push at walking pace non-stop towards the total station. And as we go, we'll see live on the control units our current chainage, the slew, and also the uplift on the left and right rail. We can also see main geometry points as we pass over them, shown in the box with main points highlighted in red on the lower left of the screen. And we also get a live update of cant and gauge difference as well as we push along the track. Once we have the prism TMD adjacent to the instrument, we simply unlock the instrument TMD, move it to our next reference point, take a measurement, and then measure back. So we don't need to measure the two chords again, we just need to measure the end of each chord as we push along. Again, that saves time and improves productivity. So once we've measured the data in the field, we take the information off of the control unit. There's a folder created called measure, and within that, that's our measured file there. So we would take that data file, off the controller and put it into GeoTamp software to create the tamper file, the front offset file. Okay, so again, we've got a series of screen grabs here talking through the GeoTamp software. So we would create a new project, and then we would import the data. And the first screen that we see here shows us the measurement information in a tabular form. So we can see the reference points that we measured against, the chainage, the horizontal and vertical differences, and the cant error. And we can also correct any errors at this stage if we want to. We can delete points if we've measured them in error. If we've had to move the TMD off track and put it back on, for example, we could delete those points. We can also view that data in the graphics view as well. So the four views that you can see in front of you, the outer views coloured in green, those show the original data as measured in the logger. And then the two inner screens show the data that we're actually working with. So if we were to delete or move points, we would see which ones have been moved by the original copies on either outer side there. The screen on the middle left, if you like, shows the horizontal measurements versus design, and the one on the right shows the vertical measurements versus design. And we can see the straight line there, that's actually our design line that we're seeing. So we would click into tamping mode, and now we can see that the screen on the left shows us the horizontal measurement versus design. The middle screen shows us the vertical measurement versus design, and the right screen shows us the cant error of the track. And now we would create our ramp to create our front offset file for the tamping run that we wish to achieve. You'll also notice on the screen there are various wiggly coloured lines. On the left screen, the red outer line shows the maximum slewing capacity of the tamper. The middle screen, the first yellow line to the left shows the minimum uplift of the tamper. The red line shows the maximum uplift of the tamper, and the blue line shows us the ideal line that we like to achieve. So that's keeping it 20 mil low to design. So we're now going to create our tamping run by defining our ramps. So if we do the horizontal one first, you can see that I've started from a measured point on the track and run into the design. I'm now running along the design, and then we'll run out again at the top end. And you can see by the red lines that we're well within the capacity of the tamper there to slew to design. We can also do the same thing with the vertical elements as well. So you can see that I've started from the existing measurement, run on to the 20 mil low vertical line, run along that, and then tamped out at the end. And you can also see right at the bottom of the screen there, you can see there's quite a jump in terms of lift. This is ramping back into an existing section of track. So we're around 80 mil, 90 mil low. But it will take a couple of tamping runs to get there from a vertical perspective. So once we've defined our tamping ramps, we can export that data. So I'll click on Export and Tamping Data. I can save that file. It then asks me if I want to interpolate a grid. So I can select the grid interval at which I want that front offset file to be created, and then I can click OK. That file is then created along with a text file. You can see two on the screen there. So we'll take the front offset file onto the USB stick to plug into a tamper, and then the text file that's also created is just for the benefit of the guys sat in the tamper really, so we can see what chainage we're at, the slew, and the uplift. We can also see where we need to go versus target. So on the target there, we can see that the 0 means that from a horizontal point of view, we're going to get to design, and then we're going to remain 20 mil low to design from a vertical point of view. We can see the cant error and also the measured gauge as well. As part of GEOTAMP, we can also create track geometry reports. This particular one is a standard report used in Germany, and this will give information including things like twists, either in a text format or also we can see it in graphical format here as well. A new report that we were asked to create with Network Rail is the speed rater chart. So what we've done here is take Network Rail's construction standards and embed them into the export format from GEOTAMP. What we can see on the first screen here is the various speed bands that that track is fit for. This particular example here is shown in a variety of different speed bands just to show you how they're variously coloured. But the next slide here will show how it actually should look in reality. So we can see it from a tabular and also from a graphical point of view. And we can also see what elements of that track is causing the speed issues. So we can see whether it's a slewing issue, a lifting issue, delta cant, a twist or a gauge, coloured accordingly. So we're split down here into speed bands, below 20, 25 to 40, 45 to 60 and so on. And I can see here that we would be good to open this track at 60 miles an hour without any problem. We could in reality probably open it to around 75 miles an hour, but because of a slewing issue at these two chainages here, we can't open it beyond 95. We could at that point decide, okay, we'll go to these two chainages, slew the track over and remeasure this particular section of track and then open it up to a higher line speed. Or we could choose to say, okay, well, we're happy to open it at 60 now, and we've got the documentation to sign off on that. So the workflow then for the tamping process with the GEOVORSA system is to prepare the data in GEOOffice, copy it onto the GEOVORSA system, process the measured data in GEOTAMP software, and then either export to the tamping machine and also create our quality report documentation as well. If we look at comparing various systems available, either manual measurements, MSAT and curve laser, GEOTRACK, which is using a single track measuring device in conventional mode with a total station on a tripod, or GEOVORSA. So I thought it was interesting just to compare how they stack up really. So we can see from a track block point of view, do we need to block the track? The exit time to come off the track if other vehicles need to pass or the machines need to come along. How many personnel are required to operate the equipment? The accuracy, the data flow, typical measurement performance, and how flexible is the system. So we can see here we do require a block with the MSAT. We can't get it off track if we need to. We've got quite a high level of personnel if we're looking at working manually, not as accurate, and an analog method. We also see the measurement performance between 250 and 350 meters an hour versus the others. 600 meters per hour with GEOTRACK, but even then we're not up to the speeds of VORSUS or MSAT and curve laser. We also see that the others offer quite a bit of flexibility on track, whereas the machines can't be moved. So in terms of productivity then, we can see that the VORSA system in Germany has 95% market share for pre-measuring. There's 45 plus systems in operation worldwide. And the latest upgrade for kinematic mode takes it from 1.2 kilometers an hour to more than 1.5. In fact, the speed record set last year for VORSA survey teams recorded more than 2 kilometers an hour. To sum up some of the benefits of the system, we support any coordinated site grid, pure relative mode and absolute track geometry. A very flexible system. We moved on and off site to accommodate traffic. We can switch between measuring multiple roads work day or night, and the data flow is digital, from design to as built, reducing human error and improving accuracy and longer lifespan for the track assets. We can also see that when we're combining horses with machine control, the process on site is even smoother. Some additional benefits. We're increasing productivity. Essentially, the tamper can work continuously. The ballast consumption can be estimated in advance. Track blocking time can be reduced. And the results can be provided online by measuring behind the tamper as well. So we can pre-measure in front of the tamper, check the speed razor information, give him the ALC file and get him working, and then follow on behind measuring the as-built as he goes. The system can be used very flexibly, enabling better site logistics. And on average, we're seeing from reports of systems used around the world, 30% or even higher productivity increases. So in summary, from a Borsa's point of view, I hope you've seen over the last few slides the benefits of taking the digital design through to completion using machine control and judo Borsas. I thought I'd just take this opportunity also just to mention a few things with regard to Railtex. We will be exhibiting there next week from Tuesday to Thursday on stand F34. We'll be very, very pleased to see you if you're attending the show. We'll be taking the opportunity to unveil a few new products and services. We'll have all our relevant rail staff in attendance from machine control mapping and myself. We'll be launching the new Judo 2 track measuring device. It will have its UK premiere at Railtex, including the new Judo scan option, both field software and office software. In addition, we're very, very pleased to announce our distribution partnership with Imatrim, where we're looking at video monitoring for looking at a variety of displacements, including structures, but importantly also looking at real-time live track deflection under traffic. So we'll have that system there. I'll be very happy to talk to you about that. We'll also have Martin Palmer attending the show from our mapping business area, and he'll be on hand to talk about the latest developments in handheld GIS data collection, but also the geospatial side of our business, so the 3D laser scanning vehicle and also our UAVs. Pete Brooks and Andy McCann from our 3D machine control business area will also be on hand to chat about the latest innovations with the GCS system. I know from a 3D dosing point of view, the equipment's widely adopted. We also have some really fantastic innovations for the 3D excavators as well. So please do come by and talk to Andy and Pete about that. So just remains for me to say thank you very much for attending this morning. Apologise for a few technical glitches at the start, but hopefully it went okay from then on. And if there are any questions, I'd be very happy to answer them now.
Okay, thanks Matthew. We've had a couple of questions, so we'll get straight into them. First of all, Mike asks, how many Borsa systems are being used in the UK?
Well, at the moment we have sold a system which is going to be used very shortly. The Borsa system was approved by Network Rail towards the end of the summer last year, and so although we have sort of talked about it for a little while now, it is really still quite new to the UK market, and at the moment we're doing quite a lot of demonstrations and evaluations to prove the system. We're working closely with Network Rail and also their main subcontractors as well, Babcock's, Babcock's, KOREC Rail. So we're hoping to see some kit adopted in the UK very soon. As I say, we have sold a system already, and we have got a number of single TMD systems that are in use in the UK already, and their users are looking to upgrade to Borsa systems. So watch this space.
Okay, we've got a question here from Michelle, who asks what training is supplied with the equipment?
It depends on users' requirements, really. One of the other benefits of the Vorsa system is it's not designed, or it wasn't originally designed to be used by surveying engineers. It was designed to be used by trackmen. Essentially, we're creating a digital HALAD survey, really. So if you've got no total station experience and you simply want to use the Vorsa system on its own, you're not interested in survey practice like traversing and checking control and that sort of thing, a couple of days of training would see you using that kit quite happily. If you want to go through sort of survey training as well, then we'd add another day or so to that.
Okay, a question here from Tony, who asks, what format is the survey control imported into the GEDO office? Is it CSV or a Trimble job, and can it be imported separately?
Yes, hello Tony, I saw you logging in there. Thanks for the question. It's a CSV or text file, so it would be in the format of point reference name, so it could be STN1 or A or B or C, however those control points were named, comma easting, comma northing, comma elevation. And it's just in that format, so whether it's CSV or .txt, that's absolutely fine.
Okay.
Oh, sorry, you said about it, can it be imported separately? Yes, I mean, when you go into the field software and create the project, you can bring that CSV file in from a memory stick. It doesn't need to go into GEDO Office and then onto the controller. In the next version of GEDO Office, where we start using the database function, it would make a lot of sense to do that, because then you wouldn't have to build the job in the logger. You'd simply create it on the PC first, and then drag it across onto the control unit, and everything would be set up ready to run. So yes, you can import it separately if you wish.
Okay. Another question from Tony again. Is an SD value on the report? This was crucial for the post-TAMP reports in the past.
That is a good question, and one which I shall have to defer to that, I'm afraid, because I don't know a definitive yes or no answer on that. I will find out and get back to you.
Okay. And another question from Tony, where is Railtex?
Railtex is down at Earls Court next week, from Tuesday to Thursday. We'll be there all 3 days, and we'll have the equipment on the stands, including the GEDO 2. And I know that my colleague from Trimble, Matthew Moss, will be doing a presentation down there as well. So we'll be going on to support him. So yeah, down at Earls Court.
Does anybody else have any more questions? If you just type yes, then we'll hang on for you to type.
If you do think of anything else, or if you pass the presentation on to anyone and they download it and think of any questions later, if you can email them to me, I'll be more than happy to respond to them.
Okay, so we haven't got any more questions, so we'll end the webinar there. Please do join the KOREC Rail group on LinkedIn. You can contact Matthew or myself directly. You can get up-to-date information on anything rail related from KOREC, and you can book a demonstration. If you'd like to get any more information, you can contact us directly via our website as well, or you can contact Matthew. For up-to-date information on events and future webinars, please see our Facebook, Twitter and LinkedIn pages. Thank you all for taking the time to join us this morning, and thanks to Matthew for presenting. We look forward to seeing you all on future webinars. Thanks everyone.